Okay, welcome everyone. Very warm greetings from Mercy Technologies. So we have got some introduction to tree data structure yesterday. Just a small bit of revision. Trees are also logical data structures, just like linked lists. Just like stacks and queues. Okay. Uh, so how tree looks like? It has a root and then it has child. So if it has only two children, which means maximum of two children, then that can be termed as binary tree. Okay, so most of the interview questions or most of the questions that we are going to do as part of our class are going to be in binary trees only. So we need to dig even more deeper into binary trees. But yesterday we just saw a few properties or few things of trees. I cannot say things. I can say only properties. Okay, so those are like so what is the level of a tree, what is the height of a tree, what is the degree, right, what are external nodes, what are internal nodes, etc, etc, and what is a node. We have even seen how do we represent a tree, how do we represent a tree node as well, right? So after that I told you that we will be doing traversal programs, right, just like how we did for um, linked lists. But before that, let me cover a little bit more theory, because like for example, yesterday I told you that questions can be asked in the interview or maybe in the written test, right, or in the hacker ranks. What they say is like they say external nodes, or maybe they say some in order traversal, pre-order traversal, right, or they can say something else. So what I want to make sure is like I want to give all the theory to you guys, because there shouldn't be any confusion at all as you move forward. So that's why let's do a little bit of more theory today, and we will be seeing about the following in this class. So what is that? We'll be seeing about the type of binary trees. Like when I say binary tree means the maximum number of children a node can have is equal to 2, so which means it can have 0 children, or it can have a 1 child, or it can have 2 child, not more than that. Okay, a 0, 1 or 2. Only these three are the possible cases. So then I will be teaching you about the binary tree traversals. I can say not the binary tree, but we can generically say that as a tree traversal. But here we are confining that to binary tree traversal. Okay, so what are the different types of binary tree traversals? We will be looking into those also. Okay, straight away without wasting time, I would like to just start with the binary tree types. Okay, binary tree types. So what is a binary tree, guys? Binary tree is nothing but it has maximum of two children. Okay, it has maximum of two children. So let's see what is a strict binary tree. Strict binary tree is it has 0 or 2 children. Like I told you, the binary tree maximum number is 2, which means it can either have 0 or 1 or 2. But in a strict binary tree, so the children should be either 0 or 2, which means either it should not have any children, or if it has, it should have two children. Okay, so what is a full binary tree? Full binary tree is nothing but all levels should be filled, right, which means, for example, yesterday we saw what is a level, right, what is a level of a tree. So that level should be filled in the sense, for example, let's say it has only a single level, which means the number of elements should be three. One is the root, second is left child, and third is right child. We'll be seeing more examples, but this is one more thing: all levels should be filled. What is a complete binary tree? All levels except the last level should be filled, or I can say can be filled. Okay, all levels except the last level can be filled. Okay, this is the property of a complete binary tree. So we'll see one more time, guys. Just try putting this into your mind. Binary tree is nothing but it has maximum of two children. Strict binary tree is nothing but it has either 0 or 2 children. Full binary tree is all levels should be filled, and a complete binary tree is all levels except the last level is to be filled. All levels except the last level is to be filled. Okay. So with this, guys, this is a theory, or this is an understanding that we have. Let's try to move forward and try to do small exercise. Okay. So I'll be taking a few trees. Okay, I'll be taking a few examples of trees. So with this, maybe I'll try filling this. I'll be try filling this this table. So with this, what we need to understand is like we need to justify if that tree is a binary tree, is it a full binary tree, like that kind of a justification we need to give. So with that, we will be in a position to actually understand that yes, we have done something which is good. So right guys, let me take the examples one by one straight away. I'll be going back to my whiteboard. Just a second. So here it is. I can say something like this. Yeah. So let me copy the properties of trees as well. We have done till now, right? Let me copy that as well. So what is that? So what it says, it is common. No, not this. Yeah. This. Okay. So let's try to analyze, guys. Let's try to analyze. Since you have a pen and paper, that's fine. People can take examples on the notes, or if you do not have, just by seeing the screen, you can give me some answers to it. Okay. Let's try to see. I'm taking one small example over here. Maybe I'm taking one small example over here. So what is this? This has only a single node. It doesn't have a child. It has nothing. So with this I just want you to go through these properties and say we will be filling this table one by one. Okay, so what I say, is it a binary tree? It has maximum of two children. Maximum of two children in the sense like it has no child itself, so which means it's a binary tree, right? Now let's move forward. So is this a strict binary tree? It has zero or two children. It has no children at all. Okay, or two children, right? Or two children, it has no children, the first condition is satisfied. So let's say this is a strict binary tree. So what is a full binary tree? All levels should be filled. This is only one level, right? There is no extra level to it. It has only one level and all levels are filled, so which means I can say that this is a full binary tree also. Okay, and then I'd like to check for a complete binary tree. All levels except the last level should be filled, or I can say it can be filled, whatever. All levels except the last level can be filled. So this is the only one level. Okay, only one level, and that level which is already present here is already filled because this is the maximum, or maybe this is the root, it has only a single level, so this is the maximum that can be filled, so I can say it is a complete binary tree. Okay, complete binary tree. So let me take one more small example, right? What is that one more small example saying? A tree is like this somehow, right? Guys, start replying me. Let's see. Okay, so what is that? Is it a binary tree? Is it a binary tree? Is it a binary tree, guys? Guys, able to hear me? Okay, okay. So it says yes, it is a binary tree. Let's take one by one, step by step. Okay, let's take one by one, step by step. So first thing, is it a binary tree? Yes, it has only how many children? Only how many children? It has only two children. That is a max, right? So it is a binary tree. Okay, it's a binary tree. Now I'm saying one more thing, like, is it a strict binary tree? Is it a strict binary tree? Or maybe you can start filling the table, then we can actually you can cross check as well. You can cross check as well. Okay, so let's see if it is a strict binary tree. So what is this? Is it a strict binary tree? Is it a strict binary tree? That's correct, because has only 0 2 children, and that's yes. Is it a full binary tree? Is it a full binary tree? And yes, it is a full binary tree. The reason is all levels should be filled, and it has only, like, these are the levels it has, and that levels are already filled, right? Is it a complete binary tree? Yes, it is a complete binary tree, because all levels except the last level, can be filled. Okay, which means all levels are already filled except the last level. Last level can either be filled or it cannot be filled. That's fine. So which means this is a complete binary tree as well. Okay, let me take one more example. Okay, let me take one more example. So what is this example saying? Okay, this is our example, our current example is. So let's say, is this a binary tree? Is this a binary tree? Yes, it is a binary tree because it has maximum of 2 children, right? For every node, or every node, it has a maximum of 2 children, right? Now, is it a strict binary tree? Has either 0 or 2 children. Every node, it has 2, and it has 0, 0, 0. So it means this property is fine, right? Full binary tree means all levels should be filled, right? Is it a full binary tree, guys? Is it a full binary tree? The example that we have taken now. It's not a full binary tree. Okay, it's not a full binary tree. The reason is there is one level. And this is not filled yet, right? This is not filled yet. So I can say it is not a full binary tree. No. So is it a complete binary tree? Is it a complete binary tree? All levels except the last level can be filled. All levels except the last level can be filled. This is the last level. This is the last level. This last level itself is not filled, but all the other levels are filled properly, right? So with this, what I can say is this is a complete binary tree. Okay. So now let's move forward with one more example. Okay. Maybe let me think of any other example. So what I want to say is something like this. Okay, so again it can be something like this. Okay, again I'm saying it is something like this. Okay, yeah. So is it a binary tree, guys? Is it a binary tree? Yes, it's a binary tree. Yes, it's a binary tree. Yes. Is it a strict binary tree? Is it a strict binary tree? What is strict binary tree saying? Has 0 or 2 children, right? Has 0 or 2 children. So every node either has 0 children or 2 children, right? So which means it's a strict binary tree. So now full binary tree, all levels except the last level. Oh, okay, what is a full binary tree? All levels should be filled. The last level is not filled, right? The last level is not filled. So which means I can say it's not a full binary tree. Okay, so now final one, complete binary tree. All levels except the last level should be filled. All levels except the last level. Only the last level is not filled. All the other levels are filled, right? So which means I can say that this is a complete binary tree, right? It is a complete binary tree. Let me take one more example. Okay, let me take one more example. This is a simple example, guys. Okay, what is this? Okay, is it a binary tree? Is it a binary tree? Yes, it's a binary tree. Okay, is it a strict binary tree? Is it a strict binary tree? Read the property again. It has either 0 or 2 children. Is it a strict binary tree? Yeah, it's not a strict binary tree. The reason is it has one child, right? It has only one child. The strict binary tree says it has 0 or 2 children, right? But it has one child, so it means it is not a strict binary tree. It's not a strict binary tree. Okay, is it a full binary tree? Is it a full binary tree? Yeah, it's not a full binary tree also. The reason why it is not a full binary tree is this last level is not filled yet. Okay, there is one more child which can be accommodated. It's not filled yet. So it's not a full binary tree. So is it a complete binary tree? So is it a complete binary tree? Is it a complete binary tree, guys? All levels except the last level can be filled. All levels except the last level can be filled. Read about the property again and let's see. Except the last level can be filled, right? Yes. So which means what we can conclude, what we can do, it has only two levels. The first level is already filled, right? First level is already filled, and the second level when you come, it is not filled, right? It is not filled. Which means what I can say is all levels except the last level can be filled. Which means my example that I've taken over here is it is a complete binary. Sorry, all levels except the last level. Yeah, it is all levels except the last level can be filled, so I can say that is a complete binary tree. Okay, now let's take one more example. Let's take one more small example, something like this. I want to say, sorry, maybe I'll take the normal color. Yeah, so now guys, is it a binary tree? Is it a binary tree? Yes, it's a binary tree. Is it a strict binary tree? It has 0 or 2 children. Yes, it is a strict binary tree. Is it a full binary tree? All levels should be filled. Yes, it's a full binary tree. Is it a complete binary tree? Is it a complete binary tree? Yes, it is a complete binary tree because all levels except the last level can be filled. Right? Simple. So simple. Now, one more small example. One more small example. So what this example looks like is something like this. Okay, I'm taking it here, and maybe I'm doing it like this. Okay, and then I'm doing it here. Here. Okay, this is one more example, guys. This is one more example. Now, is it a binary tree? Yes, it is a binary tree. Okay, is it a strict binary tree? 0 or 2 children. 0 or 2 children, right? Is it a strict binary tree? Is it a strict binary tree, guys? Every node has either 0 or 2 children, right? Perfect. That's not a strict binary tree. Okay, now is it a full binary tree? Is this a full binary tree? No, obviously it's not, right? Now, is this a complete binary tree? All levels except the last level, except the last level. All levels except the last level can be filled. So is it a complete binary tree? Okay, it's correct. Oh, sorry, I can say it to be like this. Okay, so now let's go to one more example. Okay, so what is our one more example saying? Yeah, this is our one more example, guys. Is it a strict binary tree? Is it a binary tree? No, it's not a binary tree. So if it's not a binary tree, then there's no point of analyzing all these three, right? Then there's no point of analyzing all these three. Let's go with the last example. This let's go with the last example. What is the last example saying? Maybe it says something like this. Yeah. So is it a binary tree? Yes. So is it a strict binary tree? Is it a strict binary tree? Yes, it is a strict binary. The reason is it has either it has 0 or 2 children. Yes, let me add this. Yeah. So okay, maybe, yeah, I'm marking it like this, right? Okay, now is it a full binary tree? All levels should be filled. It's not. It's not a full binary tree, right? It's not a full binary tree, correct? Okay. So now last thing, is it a complete binary tree? Is it a complete binary tree? Is it a complete binary tree? It says yes. Okay. Yeah. So I can say something like this. So here there is one important point to be considered, guys. We have learned it in this way. So I would like to just tweak some example, small thing over here. So that small thing would be the complete binary tree. All levels except the last level should be filled. Where I say all levels except the last level should be filled, the filling should be from left to right. Okay, the filling should be from left to right. Filling should be from left to right. When I say filling should be left to right, filling should be left to right. For example, let's say there is something like this. Okay, there is something like this, which means if this is not there and if this is filled, right, if this is filled, then that is also not considered as a complete binary tree. For example, in our case is it a complete binary tree? We said it's a complete binary tree because all levels except the last level should be filled, but the thing is, like, first my left child should be filled, and only after that it should come to the right child, which means if left child is not filled, which means obviously I can say that it is not a complete binary tree, because even though that level is half filled, the first filling should be doing on the left child. So which means I can say even this, right? I can say even this, even is not, this is not a complete binary tree. Similar case is with this also. Similar cases with this also. So what it says, this is also not a complete binary tree. The reason is, I told you, level filling should be from left to right, right? Level filling should be from left to right. Here the left one, here this one, something like this, right? This is not done, this is not done. So that's the reason, even though it is filled, even though if it can be filled, I mean to say, the filling should be from left to right, which means I can even cross out this also, right? I can cross out this also with the new property that I told. Okay. So and then there is one more thing, there is this one more thing, which is a last one here also. The filling should be from left to right. Here the left part is done, but the right part is not done yet. Right part is not done yet. So all levels except the last level should be filled. So this property itself is not, because this level is not filled itself, right? This level is not filled itself, which means it's never going to be a complete binary. What I want to tell at this particular point is, the filling, all levels except the last level can be filled, and the filling should be from left to right. That's it. So this is one important theory that we need to actually understand, guys. Understand, because this itself is an interview question. Maybe an interviewer asks you, like, is it a strict binary tree, or is it a full binary tree, etc., etc., etc. So you need to be clear on the theory, and we have taken examples till now, right? We have done this all collaboratively. Just want to ask at this point, guys. Now, what is our next point, guys? I told you we'll be doing a little bit more theory, right? So what I want to do is, I want to do something like this. Maybe I'll go back. Okay. So what I want to do is, maybe I'll bring this. Yeah. So there is one more little bit of small exercise that we are going to do, guys. Let me put that also here. So what is that? Sorry. Uh, yeah. There's one more exercise that we are going to do. So what is that one more exercise? Let me introduce that to you. Maybe I'll put it over here. This can be put over here. Okay, these are the conditions that we have on the right side, and this is the table that we are going to fill. Okay, this is just some logical reasoning, we can say. Okay, this is something that we are going to fill. So first thing is, all binary trees are strict binary trees. Is it true or false? All binary trees are strict binary trees. Is it true or false? Okay, yeah, it's false. Right, straight away there can be a tree with which is having only a single child also, but strict binary tree says either it should be, 0 or 2 child, so which means it is false, right? It is false, right? So now next one, all strict binary trees are binary trees. Is this true? All strict binary trees are binary trees. Yes, it is true, because if it's a binary tree, if it's a strict binary tree, whatever binary tree it is, it's a binary tree, right? So it is true. So let's go to next one. All full binary trees are binary trees. This is also similar. All full binary trees are binary trees. This is also true, right? Let's go to the next one. All complete binary trees are binary trees. Is that correct? All complete binary trees are binary trees, right? That is also correct, because whatever binary tree it is, like it is a, what, even if it is a strict, full or complete, it is going to be a binary tree itself. So I can say this is also true. Okay, now let's go to, all binary trees are strict binary trees. I think it's the same one that I've written, right? I think so. We can say the first one, it is, sorry, so it's false again. Okay, so now all full binary trees are strict binary trees. Is this true or false? All full binary trees are strict binary trees. All full binary trees are strict binary trees. Is it true or false? Yeah, it's true. We can correlate that with the example that we have taken previously, right? It is true, right? Next one, all full binary trees are strict binary trees. Is this one true? All full binary trees are strict binary trees. All full binary trees are strict binary trees. Is this true? It is obviously true, right? Skipped one. Oh, I skipped one. All strict binary trees are full binary. Uh, did I skip one, Tanmay? No, right? All strict binary trees are full binary trees. Yeah. So all full binary trees are strict binary trees. Is this correct or not? It is true, right? It is true. Just cross check the properties case. You will be able to know. So all complete binary trees are strict binary trees. Is this correct or not? All complete binary trees are strict binary trees. Just correlate, take examples. All complete binary trees, okay, are strict binary trees. This cannot be happen, right? This cannot be happen, because let's say if it's a complete binary tree, then it can have a single child also, but strict binary tree has only, max either 0 or 2 children, which means this is false. Okay, all complete binary trees are binary trees. Is this correct? This is obviously, it's a straightforward one. It's a straightforward one, which means it's true. And the final one, all strict binary trees are complete binary trees. Is that correct? Strict binary trees either has 0 or 2 children. Complete binary trees, all levels are filled except the last level, which means it is false, right? Correct? Yes. So this is a small little bit more exercise that we have done. One more exercise that we have done, guys. So I just want to ask, so strict binary tree and a full binary tree. Let's take an example. Strict binary tree says has 0 or 2 children. One example can be this, right? One example can be this. Second example can be this. Okay. Third example can be this. Okay. Fourth example can be this. I mean to say I'm doing the same thing. So fifth example can be this. It has only one property. What it says, 0 or 2 children, right? It has 0 or 2 children. However it goes, that's not our mind, right? That's not in our mind exactly. Which means it has 0 or 2 children. So what is the next one that you asked? So next one you asked was a full binary tree. So full binary tree is something like this. Full binary tree also we can take examples. Okay. So what is full binary tree saying? Full binary tree, all levels should be filled. All levels should be filled. So the tree can something be like this only. So in the same example, if we take, the tree should be like this, right? It should be like this, which means all levels should be filled, right? It has become very compact. What I want to say is every child should have 2 children for sure. So that's the reason it is called as a full binary tree. So all levels should be filled. Complete binary tree, so I told you the completion can be from left to right. So that's why our tree can be something like this. Okay. So this is called as a complete binary tree, but this is not called as a complete binary tree. Okay. This is not a complete binary tree. Okay, this is not a complete binary tree. The reason is the filling. Maybe this is also not filled. This is not also not filled. This is not a complete binary tree. The reason is it has been filled from, but the left one is missing, right? So I can do one more thing here. So what is this? This is one more. Okay, I have something like this. But this one is a complete binary tree. The reason is, like, the last level is only not filled, but it is not filled from left to right, right? So which means left is fine, but right is not filled. So even though it is called as a complete binary tree. So this is a small bit of explanation that is given to you. So maybe with this, if you do the exercise once more, you should be in a position to answer it in a proper way. Okay. So understood, guys? Are you able to understand? All strict binary trees are full binary trees. False. Please repeat. Okay. All strict binary trees are full binary tree. All strict binary trees are full binary trees. Okay, fine. All strict binary trees are full binary trees. Let's see. So what is the strict binary tree saying? It has 0 or 2 children. And what is full binary tree saying? Full binary tree is saying all levels should be filled. All levels should be. All strict binary trees are. So what is the sixth one? 1, 2, 3, 4, 5, 6. All strict binary trees are full binary trees. So we can take a strict binary tree. It need not be a full binary tree, right? All strict binary trees are full binary trees. This is a very good observation. So this is not true, but this is false. Sorry, I can write it in this way. So this is false. Okay, maybe we skipped it or we did it in a different way, but yeah, you're correct, Rishikesh. Okay. uh yeah, so let's move forward with the class today. Okay, move forward with the class today. So what is the one that we need to do again? Let me go to my agenda. Okay, so what is my agenda? We were done with our exercise, that's fine. Okay, agenda was this. We should see about the types of tree traversals, right? We should see about the types of tree traversals. I think yesterday I have introduced those types of tree traversals, what those are. So there are 3 tree traversals there. Those are what do you call, in order traversal, pre-order traversal, and post order traversal. Okay, post order traversal. Let me give more detailing about this to you as we move forward. Okay, so in order traversal, pre-order traversal, and post order traversal. So I was taking an example of how we solved linked lists, right? How we solved linked lists. So in the same way, we need to do our first program should be of our first program should be of traversing, right? I'd like to just repeat once more what we did in linked list, right? In linked list, our linked list used to be something like this. Okay, something like this, something like this, right? Okay, this is null, right? This head. Okay, so how do we parse, guys? So I told you that there is a link from our left node to the next node. And how did we parse? We did something like this, right? While p is not equal to null, right? While p is not equal to null, we did something like this: system dot out dot println of p dot data, and we said p is equal to p dot next, something like this. We did that until the p is not equal to null. I think I have given more explanation to you. What my actual intention is, I was moving from left to right until at one particular point. What is that particular point? Until I have my reference of that particular point. That is what we have done. Now let's move forward. Any problem, guys? Hello? Okay, let me mute everyone. Just a second. Okay. Yes, I muted everyone, right? Okay, so what we did is I have taken a linked list which we did previously, and how we did that, we have parsed. We started from head, we went until null, and we did something like this. While p is not equal to null, we did this system dot println p dot data, and we did p is equal to p dot next, right? This is what we have done. Now my question is, if something like this we need to parse, right? I told you we have something like this one. Maybe I'll take a different color. Okay, just a second. Okay, maybe I'm taking a different color. Okay, so our tree was something like this. We are dealing with a binary tree, right? 1 2 3, let's say 4 or 5. Okay, so this is how my tree was looking. Let's say I need to parse this tree. I need to parse this tree. So, or maybe I need to traverse this tree. So in this only I was saying I have three options, right? I have three options. First thing is pre-order, and the second thing is in order, and the third thing is post order. Okay, so this is the third thing that I have. Okay, so but there is only one way in our linked list, which is coming from head and going to null. In our trees, in our binary tree specifically, there are three ways. First thing is pre-order, second thing is in order, third thing is post order. This is important, guys. Please put your mind, like all concentration here. So let's try to solve an example or try to see how it goes. Okay, so this is a small example that I'm taking. Okay, so what is my small example? Something like this. It has two. Okay, it has 2 as the root, and now there is 3 over here, right? And then there is 4 over here, right? Then there is 5 6. Okay, this is a small tree, binary tree that I've taken. Okay, this is a small binary tree that I have taken. This is my binary tree that I've taken. I need to parse it, right? I need to traverse it. So first option that I have is pre-order. Second option I have is in order, And the third option I have is post order. So what is my pre-order saying? My pre-order saying, I'll write once more. My pre-order is saying it is a property of root, left child, and right child. So which means the first priority, or first I will print root. First I'll print root, okay, and then I'll print left child, and then I'll print right child. My second one says first I will print left child, second I'll print root, and third I'll print right child. Okay, and my third example says first I will print left child, second I'll print right child, third I'll print root. Okay, forget about this big example, guys. Let's take a small example, something like this. What is this? 1, 2, and 3. Okay, so let's say this is a very small tree. What is my very small tree saying? So if it is a pre-order traversal, what it says, it first prints root. So which means in my first case, it first prints root. Okay, second it prints left child, which is 2, and third it prints right child, which is 3. Okay, in my second case, it first prints left child. So what is my left child? Left child is 2, right? Left child is 2. So then it prints root, and then it prints right child, then it prints right child, which is 3. Okay, and my third condition, first it prints left child, which is 2, second it prints root, which is 1. Second it prints right child, which is 3, and third it prints root. Right, so this is a small example. Just by taking this example, right, just by taking this example, we are able to conclude that this is how the traversal works for a very small example. So at this point, guys, I just want to ask if you understood this traversals. Right, we have taken that example, guys. Let me just repeat the previous one. So what is this? The pre-order, in order, and post order. Pre-order says we should be printing root first, then we should go for left child and right child. So my in order says left child, root, and right child. My post order says left child, root, and left child, right child, and root. So this is how the printing order, this is how the traversing order should go. So with the example that we have done, so we came to know that the pre-order comes to 2, 3, 5, 6, 4. Second one, it comes to 5, 3, 6, 2, 4, and third one 5, 6, 3, 4, 2. This is a small example. So now I've given a small assignment. So what is that? This is the one. This is a small example that I've taken till now. So this small example, I want you to give me the answers. Okay. Okay. So I got answers from people. I got answers from Lata. I got answers from Apurva, Rishikesh, okay, Daniel. So most of my I'm getting answers, right? So I don't know, like, if this is confusing to you guys. I don't know if this is confusing to you. Let me tell you a shortcut. Let me tell you a shortcut for this. Okay. So for the people who have already done that, or maybe for the people who are doing that in their notepad or something, so you can do with this shortcut, right? What is this shortcut say? I need to do some, careful guys, like, hear this properly so that we can do. Okay, so what is my pre-order thing? Pre-order is something, but for example, let's say I have some dash that I'm writing over here. Okay, so I'll put a dash to every node. Okay, I'll put a dash to every node. Okay, I'll put a dash to every node, guys. Okay, so I'll put a dash to every node. Now again, I'll put one more color. Let's say I put a vertical line to every node, something like this. Vertical line to every node, something like this. Okay, so I'll take one more color. For example, let's say I'm trying to put the right side line to every node. Okay, right side line to every node. Okay, perfect. So here what I will be doing is maybe I'll take something like this. So what is that? Here I'll be taking something like this. I need to start from my root. and I'll be coming something like this. Okay. I'll be coming something like this. Okay, this is how I came. Okay, this is how I came. Now let's try to write answers for pre-order, in-order, and post-order. What is pre-order? Pre-order is nothing but I have taken a black line, right? This black line. So this line that I have taken, this line or the boundary that I have drawn at the last. So whatever encounters this line in the sequence, that will become my pre-order. So what is this? First one came, right? One, and then two came, right? Two, and then four. Okay, and then 4. What is my next black line which came? Is 5. So what is my next black line? It's 6. So what is my next black line? So it is 3. My next black line, which is 7. Right? Done. 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. This becomes my pre-order. Let me tell you, in order, whatever is the concurrence, or whatever my final line comes and meets this blue line, will become my in order, right? Will become my in order. So what is my in order? In order is nothing but 4, right? And then 2, and then 6, right? And then 5, right? Then 1 3 7, right? 4 2 6 5 1 3 7. So what is my post order? My post order is nothing but wherever my line comes and encounters my green line, that becomes my post order. So what is my post order? 4, right? 4, and then 6, and then 5, and then 2, and then 7 3 1, right? This becomes my post order. Simple, guys. This is how, using this shortcut, however complex your tree is, you can print your pre-order, post order, and what you call your order traversals. You can see something. Okay, so using this example, you can take however complex tree you have, and then you can give me the pre-order, post-order, and in-order traversals. Let me give you one last example. Use the shortcut, or maybe for the people who have done previously, let me check what are the answers that they have given. So let's see what are the answers that they have given. They have given answers something like this. Okay, where is that? You can cross check your answers, guys. You can cross check your answers. So okay, you can cross check your answers, and finally you just conclude if you are able to do it properly or not. Now let me take one more small example. And I want answers from most of you guys. Okay, so, or maybe let's cross check if this is working with our previous example. So what I told, right? With the same example, let's try to see if our previous example is working or not. For pre-order traversals, the line which encounters all my left things should be printed 2, 3, 5, 6, 4, 2, 3, 5, 6, 4. That's fine. So here for the vertical lines, it should be concluding. So what is 5, 3, 6, 2, 4, 5, 3, 6, 2, 4? That's fine. On the left lines, it should be encountering, which is this 5, and then 6, and then 3, and then 4, and then 2. That's it. So this is how we got our post order, right? We just cross checked also, it was working. So now what I want to say is, I'll be giving you a small example. Let's try to see, if everyone is able to answer this or not. Okay, 1 2 3 4 5 6 7 8. Right, this is the tree that is given to me, guys. I want answers for pre-order, in order, and post order. So what are the answers for these? You can start typing, guys. I need answers from you guys using the shortcut that we have done. we should be in a position to actually calculate it very fast. Okay. Yes, you guys are doing pre-order perfectly. Let me try to draw those things also here. What is this? This is one. Right. There's one more. Let's say I have something like this. Let me put it a little bit more up. So there is one more which is this. Okay. 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 Yes, good. People are giving answers. Let's do it collaboratively now. Okay. Let me try to do it once more. So what it says, here it goes. We are starting for pre-order. We should be printing all the left color, which means all the green color encountered lines. So it should be something like this, guys. So it should be something like this. So you should draw as close as possible, which means something like this. Okay, I've drawn a black line over here. Now let's mark everything. So what is that? The first one. What is our first one? It is our pre-order, which means all the left color, all the green color encountered lines. Let's see. So what is this? 1, right? And then 2, and then 3, and then 4, 4, and then 5, 6, 8, 7, right? That's it. This is my pre-order. And what is my in order? My in order is saying something like this: 1, which is 1, 2, 2, and then again it's coming, it's 4, right? 3, it's coming 6, 8, 5, 7. What is my post order saying? Post order is something like this. Again, you need to come and calculate the encountering part. So what is that? First one which will come out is 4, because my line comes and meets 4, the blue line, and then it comes and meets 8, then it comes and meets 6, right? 6, 6, and then 7, 5, 3, 2, 1. That's it, guys. These are the actual answers. Okay, these are the actual answers. Yes, I see people who are giving the correct answers, and good, guys. You are going in the perfect manner. So these are the answers. Just cross check your answers in case if your understanding is improper, then you can go back to the recordings. But this is a shortcut, guys. People find it very hard to find pre-order, in order, and post order. This is also an interview question. They give you something, they want you to at least tell the output. After that, you tell me the output first, and after that, let's see, should I actually give you the question or not. This kind of questions will come. So having something handy is very important, guys. Okay. So guys, at this point I want to ask, like, are you able to understand whatever I thought today? Great. So at this point, guys, we'll be doing program. I think we crossed our time today, but